Hello, everybody. Welcome to today's lecture. Last time we started talking about chapter 4. So we started talking about the what a discrete distribution is, and in general, what a probability distribution is. Um, and we talked about the binomial distribution in particular. That was an example of a discrete distribution. I said last time we were going to go through the rest of the examples and then go through the examples of continuous distributions, but I was kind of taking another look at it and I decided that it's not really necessary for us, so we're going to skip over that. We're going to skip right into chapter 6, where I'm going to mention briefly what a continuous distribution is because it's relevant here. And we're going to talk about a particular type of continuous distribution that's going to be very important to us. But after that, so we'll talk about that. And then after that, we'll do chapter 7. Both of these chapters are very short. Once we're done with these, we're going to be right into the heart of statistics finally. Okay, so we've been kind of taking a break from the statistics to do a little bit of probability because we need the probability to talk about statistics further. So we're going to be back into that starting in chapter 8, where we talk about confidence intervals. So give me 1 second here. Let me get my thing. Okay. So we're going to talk about 6.1. If you're looking in the book, this part is actually going to be in the introduction to chapter 6. So you want to read, if you do read in the book, you'll want to read the introduction before jumping straight into 6.1, because it actually, usually I skip over the introductions, but this one actually has some very important information about what the normal distribution actually is. So that's what chapter 6 is called, is the normal distribution. Chapter 6. Hang on. The normal distribution. So this is the singular most important type of probability distribution because it's the one that, well, for one thing, it comes up a lot. A lot of real world data is normally distributed. Like, for example, human heights, human IQ, a lot of like common things. And two, we're going to take a brief look at some theorems that involve the normal distribution. But as you go deeper into statistics, you see that there's a lot of theorems about statistics that do involve the normal distribution. So it's definitely the most important distribution. So if we're going to learn any one of them, this is it. Okay. Before we talk about the normal distribution, let's just look briefly at what a continuous distribution is. Okay, a continuous distribution remember, a distribution in general is just a function that lists all the possible probabilities you can have. Okay. So a continuous distribution is a probability distribution. And this is just in my own words. The book will have its own definition. But just for our purposes, a probability distribution which takes on an uncountable number of values. Okay. So it's a probability distribution which takes on an uncountable number of values. So if we think back to how this is different from a discrete distribution, if we look back at what we were talking about in chapter 4, right, with a discrete distribution, we could make a table like this one right here, where we list out all of the values. Like this one has 3 possible values. So we were able to list out all of them. With a continuous distribution, we could never do that because there wouldn't just be 3 of them. There's always going to be an uncountable number of them. So this makes it harder to talk about, right? A discrete distribution, if we were to graph it, like if we graphed that one, for example, like x equals 1, x equals 2, and then here would be 0. I don't remember the exact numbers, but it was something like 0.9, 0.8, 0.2 or something like that, right? Sorry, point 0.08 and 0.02 is what I meant. So when we graph it, there would be 3 dots on the graph. Okay. I'm just referring to this example right here. Yeah, it was 0.08 and 0.02. Right. So at x equals 0, your output is 0.02. At x equals 1, your probability is 0.08. At x equals 2, your probability is 0.09. So if we were to graph that, this is what it looks like, right? Just 3 dots. If we were to graph so this is discrete. If we were to graph a continuous distribution, it's going to look something like this, where it's not dots, it's a solid line. So at any particular x value you could pick, at any value for your variable, you'll have an output. Whether it's 3, whether it's 3.4567, whether it's 3.500012, etc. And you could just make that decimal as big as you want. Like you can get as precise as you want. So because of that, there's no possible way you could count all of the numbers there, because there's all of these infinite decimals and there's an infinite number of infinite decimals, right? So how do we handle something like this? Well, the standard way to do this would be, okay, if we want to find the probabilities between in like a certain region, like say from here to here, say this is x equals 1, this is x equals 2, and we're looking for the probability that x is between 1 and 2 or something like that. So it's more of a range now. It's not just one value like before when we were looking at the probability of x equals 1 or something like that. Now it's a range of values. The way we would do this is we would find the area of this region. But how do we find the area when there's a curve here, right? We could find the area if it was like a rectangle, but here there's a curve. It's not a straight line. And therein lies the problem with why we can't really talk about these too much. What we would need is tools from calculus called the integral, which, is not a prerequisite for this class, of course. So that's why we're not talking about these ones too much. So we're going to kind of have to like dance around this when we're talking about the normal distribution. But that's okay, because this is how a lot of people look at the normal distribution. It's so well studied that we're able to look at it with other ways. Without really knowing about this. Let's see, is there anything else we should say? I think that's pretty much all I want to say about what a continuous distribution is. With a discrete distribution, all of your values, or like these ones over here, when you add them up, they should add up to 1, because they show you all of the possible outcomes. Here, the area underneath the entire region should end up being 1. There's no way for us to verify that, because again, we can't find the area under a curve with our current techniques. So we're just have to kind of take it on faith with the problems that we're given, right? We're just going to have to assume that they are distributions. They'll tell us that if they are distributions. All right, so the normal distribution in particular, though, first of all, it is a continuous distribution, and it kind of looks like the one I just drew. So the normal distribution is a continuous distribution sometimes known as the bell curve. Okay, so you might have seen this before. If anything's referenced like being on a bell curve, this is what it's referring to, is the normal distribution. Um, with a probability density function, which is we abbreviate as PDF. We talked about that with the discrete ones too, discrete probability density functions. Normally, discrete ones, like I said, are called probability mass functions, and continuous ones are just called probability density functions. But it's not really too important for our purposes. So it has this as its PDF. So it's going to look weird. So don't worry, you don't need to know this. I just want to show you, this is just what the definition is. But it has, whoa, sorry, I don't know what happened there. Hang on one second. Let me get this lined up again. Okay. With the probability density function, 1 over sigma, sigma's the standard deviation, divided by the square root of 2 times pi. Okay, so it's complicated, so really don't worry about memorizing this or knowing what it is or anything. Times e to the negative 1/2 times x minus mu over sigma squared. Okay. So this is the PDF of the function, and it is pretty complicated to work with. But it's very important. It comes up in nature a lot. So it's very well studied. So because of that, there's plenty of like tables and stuff to calculate the values instead, which is what we're going to use. But we won't ever be working directly with this function. So you don't need to know this function or anything. But we do know what some of the pieces are from our previous lectures. Right? Sigma is the population, standard deviation, mu is the population mean, and then everything else is just like x is our variable. E is a number you might have seen, you might not have, but e is just a number like pi. So pi is an infinite decimal, which we approximate as 3.14, right? E is similar, except it's 2.7. I think it's 2.718. So E is like the same idea as pi. It's an irrational number. It just comes up a lot, so we give it its own special name. But like I said, we don't need to work with this. We're never going to work with this function. This is just so you know what it does look like. Okay. So if x, remember x here being our random variable, if x is normally distributed with mean mu and standard deviation sigma, then we write x tilde n mu sigma. So it's written as n mu sigma. Sometimes they might use the variance instead of the standard deviation, so it would just be that squared. So pay attention to what the problem says. But just so, for example, like if we knew we had a mean of 50 and a standard deviation of 10, we would write x is normally distributed with mean 50, standard deviation 10. So the stuff in the parentheses is just giving you some information. The graph of the normal distribution, there's a picture of it in the book, which is probably better than I can draw it, but I'll go ahead and try anyway. It's just the standard bell curve, so it looks like this. That was pretty good. The key thing about the normal distribution is that right in the center is the mean. So the mean mu. Okay. And then the book doesn't talk about this yet, but we can go ahead and talk about it. If we go one standard deviation away, so if we go here to mu plus sigma and mu minus sigma, so this distance one standard deviation away accounts for 68% of the data. Okay. So the normal distribution is a kind of distribution where the majority of our data is kind of huddled towards the center, huddled towards the mean. Okay. And the mean and the median are the same thing in this case. So you can see, like, remember, we're thinking in terms of area. If this is a bigger distance, a bigger vertical distance, there's going to be more area here. As we go this way, the area is getting smaller and smaller. So as we get further away from the mean, the amount of data that we have gets smaller and smaller and smaller. If we go out 2 standard deviations, okay, so that would be mu plus 2 times sigma to be 2 standard deviations, and mu minus 2 times sigma. Okay, that distance, that's going to be 95% of the data. 95% of the data is within 2 standard deviations of the mean. So remember the things I talked about that were normally distributed, like human height, for example. Okay, human height is normally distributed. That means if you take, say, just for instance, like the male average human height is 69.1 inches, so about 5'9". 95% of humans are within 2 standard deviations of 5'9". What exact number is that? Let me grab it for you guys. I can pull it up right here. It says in the book I used for the other class. So let me just pull that up here. I just don't remember the standard deviation off the top of my head. It's 2.9 inches. Okay, so this is male height. So mu is this, sigma equals this, 2.9. So that means if we think about 1 standard deviation away from the mean, and let's just round up here, or round the numbers, right? This is about, the average is 5'9". The standard deviation is about 3 inches. So 6'1" No, 6 foot. Or 72 inches to in the other direction, 66 inches. 68% of people fall here. 68% of males, I should say. 68% of males are between 66 and 72 inches. So that's 5'6" and 6 foot. Okay. That's pretty surprising. It doesn't seem like everyone's huddled together so much like that. If we go out one more standard deviation, 63 inches to 75 inches. Okay, 63 inches would be 5'3". Um 75 inches would be 6'3". So 95% of males are between 5'3" and 6'3". Okay. We change this to males. If we went out one more standard deviation, okay, so this would be mu plus 3 sigma. This would be mu minus 3 sigma. That's now going to account for 99.7%. Okay, I mean, that's almost everybody, right? There's only 0.3% people outside of that. So with height, that's going to be 60 inches, 78 inches. All right, so that's 5 foot to 6'6". Okay, so only 0.3% of people of males are not between 5 foot and 6'6". Okay, and also think about this is symmetric, right? This is symmetrical around the mean. So of that 0.3% that's remaining, only half of it is on both of extremes. So only 0.15% of people, 0.15% of males are taller than 6'6". Okay. And then only 0.15% of males are shorter than 5 foot. Okay. And I mean, height is just one example of something that is normally distributed. Like I said, IQ is another one. I don't think weight is in humans. It is in some other animals though. There's a lot of stuff that does end up being normally distributed. Like I said, this doesn't come up until a little bit later. But I figured we could just do it now. So let's move on now to 6.1. 6.1 talks about the standard normal distribution. Okay. So the thing with the normal distribution is that this mu and this sigma, they could be anything. And that can get kind of messy. So what we like to do is we like to take all of our values and standardize them so that our mean is always 0 and our standard deviation is always 1. So this is kind of something we commonly do in math is we take whatever we have and we center it around 0 instead. So here it's centered around some mu. It's just a mean. It's easier to work with if we just take it and center it around 0. Okay. So that's all the standard normal distribution is. Is the normal distribution with mean 0, so mu equals 0, and standard deviation 1. So sigma equals 1. And remember, sometimes I said before, sometimes people state the normal distribution in terms of the mean and variance instead of standard deviation. But the variance is just the standard deviation squared. So if the standard deviation is 1, 1 squared is still 1. So in this case, the variance and standard deviation are the same thing. Okay, so x would be normally distributed with mean 0 and standard deviation 1. So this is what the standard normal distribution is. But what if we're giving something that's normally distributed? How do we take it and make it standard normally distributed? Okay. Well, we use what's called the z-score. Okay. Let me see here. If x is normally distributed with some mean, some standard deviation, mu and sigma, then the z-score is z, so we call it z. It's going to be x minus mu divided by sigma. So we take our data value, our x, we subtract the mean, and we divide by the standard deviation. So I'll write it out in words. So z is the data value minus the mean divided by the standard deviation. Okay. So we take our normally distributed data, we find the z-scores for all of the data, and now we have a standard normal distribution for data with those z-scores. Okay. So what does the z-score actually tell us? Well, if we calculate the z-score of a data value, okay, the z-score of a data value x tells you how many standard deviations the value x is above, which if we graphed it out would be to the right of, or below, which if we graphed it out would be to the left of, the mean. Okay. So it tells you how many standard deviations away from the mean you are, essentially. So let's go back to our height. I said the human male height has mean 69.1 inches, standard deviation 2.9 inches. Okay, so let's say that somebody is let's say 5'11". Okay, so 70 inches. So somebody is 70 inches. What is their z-score? So we should expect it to be, first of all, around 1, because we know that's within 1 standard deviation based on what we did earlier. So 70 minus the mean, which is 69.1, divided by 2.9. Let's see, we're going to have 70 minus, sorry, I said 5'11", didn't I? So that'd be 71. Yeah, it's 71. 71 minus 69.1 divided by 2.9 gives us 0.65. Or I guess we could say 0.66 if we want to round it. Okay. So it's exactly 0.66, or I guess I should say approximately because we rounded 0.66 standard deviations above. So what we did earlier, we saw that it was within one standard deviation, but this tells us exactly how many standard deviations above it is. So in other words, if we took 6.91 and added 0.66 times 2.9 to it, so we go up by 0.66 standard deviations, then we should get 71. Okay. It's not going to be exact because we rounded, but let me see. We get 71.014. Okay, again, because we round it. Okay. So the z-score is it's very important here. Let's look at example 6.1 real quick. Okay, let's say x equals 1 and big X. Remember, we're using big X for like the random variable, meaning like all of the data values, and the little x is like a specific data value. Okay, so big X is normally distributed with mean 12, standard deviation 3. So the z-score, what would it be? Well, we're going to do 1 minus 12 divided by 3. Okay, 1 minus the mean divided by the standard deviation. So it's going to be negative 11 over 3, which I think is like 3 2/3. Yeah, so negative 3.67, rounded. So 1 is 3.67 standard deviations below the mean. The negative is telling us it's below. Okay. Sometimes you'll see an absolute value around the z-score to make it positive. Because the only thing like the negative is doing here is just telling us which direction we're going in. Are we below or above the mean? So that's why we didn't use it here, but sometimes you might see an absolute value because sometimes you're just interested in how far away it is, not whether it's above or below. Okay. We might even throw an absolute value on there later. So the next thing the book talks about is what I talked about up here. Okay. And I didn't say what this is called, but this is called the empirical rule. Okay. Empirical means you can tell just by looking at it, right? So just from looking at what the population mean is and what the population standard deviation is, we can tell where the data is. Okay. So definitely know how to use this graph. There will be some homework problems using this because this is really important because like I said, a lot of things are normally distributed. And yeah. So that's the end of 6.1. So the next thing we're not going to talk about a lot because it's just talking about how the most important thing for us is going to be like the z-scores, okay, and calculating the z-scores, so doing this. But the next thing, here I'll add a page for it in 6.2. Sorry. There we go. All right. So 6.2 talks about calculating the normal distribution. Like I said, we need the tools from calculus to really do that. But one way we can do it is by using either a table or Excel, okay, or a graphing calculator. So we're going to learn how to do it using a table, okay. Um, I think, yeah. Let me see if I can pull up a good table for us. Give me 1 second. Okay, actually, I'm just gonna end this video here. I'll separate 6.1 and 6.2 into separate videos. Um, so next time I'll show you guys how to do a few things. One, how to calculate the normal distribution using a table. Um, because we're using a table, that makes it even more important that we're standardizing the values. Like I said, centering around 0, because a table can't take into account any possible mean and any possible standard deviation, right? Because they could be anything. But it can take it into account if the mean is always 0 and the standard deviation is always 1. Then it's fine. So we're going to look at a table using the standard normal distribution. Okay. And then I'll show you how to do it in Excel also, as well as Google Sheets. And yeah, and then that'll be it for chapter 6. So then we'll do chapter 6 and 7 probably next time, because 7 is also pretty short, and there's not a lot we can do without going into calculus also. So yeah, so we'll finish up chapter 6 and start 7 next time. So thank you for watching this one today, and hope you have a good day.